A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm the same. Thank you. Roshan, in order to make short notes, you can virtually read all the content that you have to, and then eventually write the notes on your own. So, be it the book, the PPT, everything that you can come across, go through that, and then make your own notes. Okay, so hello, a very warm good afternoon to all of you, and welcome to Baiju's Exam Prep IAS. Welcome to another weekend of geography, where today we shall be picking up the threads where we left off last weekend. And last weekend we had been discussing about the issues, for example, in oceanography. We had started the discussion about the ocean temperature. In fact, we first of all started the discussion with the ocean bottom relief features. Then we moved ahead to discuss about the ocean temperature and how the ocean temperature indicates a variation not only in terms of one particular region to the other, that is the horizontality, but also the vertical variation. We familiarized ourselves with the terms, for example, about the thermocline. What is thermocline? So it is that zone of transition around 500 meters to 1000 meters deep in the oceanic water, where the temperature suddenly ends up declining or changing quite drastically. And that is similar in the case of salinity conditions as well, where at a particular depth, the salinity conditions, they keep on, or they actually change quite drastically, and that is what we also refer to as halocline. So basically, we had looked at the oceanic salinity as well, that what are the factors which contribute to oceanic salinity, what are the factors which inculcate a kind of an addition of water molecules or removal of water molecules, to be very precise. And there we had looked at, in terms of salinity conditions, certain examples of various different areas which have higher salinity, and also certain areas which have very low salinity conditions. Now here, while studying about salinity, we had started the discussion about the stratification of ocean waters. That when you have water of different salinity in the same region, then the water arranges itself in the form of various different layers. And that is what we refer to as the ocean stratification. We also understood that how this factor of ocean stratification can end up leading to a kind of formation of tropical cyclones or a greater heating of the surface waters in many different areas where you have a very active stratification happening. For example, Bay of Bengal. So today we shall be picking up from that. We shall be talking about the aspect of ocean water density, how it varies, what is it dependent upon. And then after looking at the density variation, we shall be looking at the circulation in the ocean water, the movement of ocean water, that is the waves, the tides that we have, and also eventually the ocean current. So those are the factors we shall be looking at today. And then after that, we shall be moving ahead with Indian geography. Okay? Ajit, I couldn't understand humidity and the types of humidity. Can you briefly explain the topic? You want me to explain the entire module, Ajit, is it? So I hope you understand that now the recordings of the PPTs are, or recordings of the sessions are also available. So in any case where you have not understood any of the aspects, you can please go through and watch through the recordings, because please understand there are other candidates in the sessions as well. It is not a one-on-one session. So with all humility, let me submit before you that if we go back to the portion of humidity, that will be a great decoupling from the portion of the class that we are carrying on. So it won't be justifiable for any of us. So that is why I would urge you, go through the portions of the recordings. If not understood, look at it from the tablet lectures. I hope you have the tablet lectures with you. Look at the tablet lectures also. If still a doubt persists, then contact me again. You can get in touch with us. We'll ensure that which is the portion which you are facing a doubt in. And anyways, I would suggest all of you that whenever you are unable to understand a particular topic, see, the very easy aspect of it will be that I have not understood that entire topic, so repeat the entire topic. Never have that approach while studying. While you are studying any particular topic, let's suppose tropical cyclones, you have not understood tropical cyclones. It cannot be the case that from point A to point Z you have not understood anything. Pinpoint which area you have not understood. Is it the rising of air? Is it the sinking of air? Is it the latent heat of condensation that you have not understood? There is invariably one point of doubt which leads to the entire context of the concept being murky. So pinpoint that doubt. It will be easier for you to solve your problems as well. It will be easier for us also to help you out in this case. Okay, Ajit? I hope that it is taken in a positive aspect. What is the doubt in humidity? Pinpoint that. And maybe we can help you out in a better way. Okay? So now we talk about the basics about the density of ocean water and what is it actually dependent upon. So when we talk about the density, what is density? When we talk about, or when you hear about the term density, what is density? Density is basically the mass per unit volume that we have. The closeness of the materials, how closely are the materials packed, that gives us an idea about density. Just a moment. So when we talk about the density, it gives us mass per unit volume or closeness of the materials, right? Now let us understand how this density varies from one region to another. Density of oceanic water. Now this is dependent on two major factors. One is the factor of temperature, and other is the factor of salinity. Okay, so one is the factor of temperature, which controls density. The other factor is that of salinity. So how? So for example, in any sample of water, let's suppose we say that the temperature is very high. What do you think will be the density of materials in that case when the temperature is very high? In that situation, what do you think? So when the temperature is very high, the materials will tend to expand, isn't it? The materials will tend to expand means what? Molecules will be moving farther away from each other. So greater the temperature, lower is the density, isn't it? So warm waters will have lower density and colder waters will have higher density always, because depending upon the temperature, the molecules will be moving away from each other or closer to each other. Anyways, we do know that anything which has greater density eventually tends to sink. Anything which has got lesser density, which is lighter, tends to end up floating. So when we talk about density in this case, in case of temperature, cold water is denser than warm water, which basically brings us to the conclusion that higher the temperature, lower is the density. So colder waters are denser, warmer waters are lighter, they are less denser. So anywhere where you have both cold and warm water, let's suppose, always the warm water will end up floating because it is less denser. Now salinity is also a controlling factor. Now when we talk about salinity, you have to understand that salinity is what? Amount of salt present in any sample kg of water. In one sample kg or 1 kg sample of water, what is the amount of salt which is prevalent? Now that can also end up varying. For example, when you have higher salinity means what? Greater amount of materials are packed into the substance. So higher salinity means greater is the density. Okay. So high salinity means higher density, and low salinity means lower density. Okay. So here, when we say high salinity is denser and low salinity is less denser or lighter. Now, let us try to elevate the concepts a bit. So when we are talking about the aspect of density, we know that it is dependent on both temperature and salinity conditions. Now let us consider a situation or a region where both these factors will be instrumental and will be at play. For example, let us take the instance of tropics. Now, in the case of the tropics, what is the temperature condition? Temperature, is it high or low? Let me know. And what is the salinity condition? So in the case of the tropics, the temperature is usually very high, right? Many of the times higher than the equatorial region. What about salinity conditions? Salinity is high or low in the case of the tropics? Highest. Very good. Salinity is highest around the region of the tropics. That is very good. So this is also very high. Okay. So temperature is very high. Salinity is very high. Now, as per this, with higher temperature, we should have lower density. But if the salinity is very high, it should indicate higher density. So in the same region, one factor is indicating the water should have lower density, and one factor is indicating that water should have a higher density. What do we think is the end result in this case? What will be the density of water in the tropics? So always understand, whenever you have both the factors at play, both the factors of temperature and salinity are at play, the temperature conditions will always predominate. The temperature conditions will always be more dominant. Why? Because it is the temperature conditions which will lead to the expansion or the contraction of the materials, the molecules. And when the materials or the molecules will tend to expand, the matter will tend to expand. That is when the density will lower. So let me write it down. Whenever both temperature and salinity conditions are involved, temperature is the dominant factor. Okay, temperature is the dominant factor. So in that case, temperature determines salinity. Okay, so that is basically the aspect of density of water. So here always you will come across the situation that the density of water at the tropics at the lower latitude will be lower. What about the density of water at higher latitudes? It will be higher. Okay, so density of water at lower latitudes will be lower, and density of water at the higher latitudes will generally be higher. Now that brings us to the concept what we refer to as a circulation due to the factors of density, right? So circulation due to the factors of density in between different latitudes. And understand this carefully, because this is something which is present, which is found to be present all across the globe. It is one of these circulations which allows for mixing of the oceanic water from one region to the other. So here, let's suppose we have the oceanic water. Let's suppose these are your lower latitudes, and these are the higher latitudes. So in this case, when we are talking about the lower latitude, the temperature will be high. So as the temperature is higher in this case, what will happen to the density? The density will be lower. So here, the heating is also very high. Now, when the heating is very high of the water, oceanic water in general, any state of matter for that aspect, any state of matter, when it is heated, it will tend to expand a bit, isn't it? So here we see that the heating of the oceanic water is much greater in the region of the lower latitude. So that means it is going to expand a bit. So that is why in the lower latitude, due to extreme heating, water tends to expand as compared to the higher latitude. And that is where water gains a kind of a height advantage as compared to the region of the higher latitude. So here basically in the lower latitude, due to heating, extreme heating, water tends to expand. So when water tends to expand, it will gain a kind of a height advantage, right? It will be ever so higher, slightly so. Now water will always move from a greater height to a lower height, always. That is the motion indicated by water, always will end up moving from a higher height to a lower height. So here, because of this height difference, water initiates a movement towards the higher latitude. Okay, so water initiates a movement towards the higher latitude. Now when water comes to the higher latitude, then what happens? Here, water will cool down, it will lose its temperature, isn't it? So at the higher latitude, water cools down. Also, significant portion of water will end up getting frozen. So when the water gets up frozen, what happens to salinity? Due to freezing of water, what is the variation in terms of salinity that we experience? Good, Pranay. Chandrakant, Shubhojit, correct. Vishal, Yera, Utkarsh, correct. Kalyani, incorrect. So freezing, whenever you have freezing, anything which freezes, in the case when water freezes, it brings about removal of water molecules from the sample. So freezing will always lead to an increase of salinity, always. Freezing brings about increase in salinity. Okay? Whenever freezing happens, it will always bring about an increase in the level of salinity. Now, the salinity level has increased. The temperature has also decreased. What will be the impact in terms of density in that case? In that case, the answer is very simple. That density will end up drastically increasing. So in the higher latitudes, you will suddenly have very high density. Very high density. Now, when you have very high density, in that case, what happens? Very high density of water means water will end up becoming heavier, isn't it? Water will end up becoming heavier. So this same water, which had come from the lower latitudes, now as it has reached the higher latitude, it has not only become very colder, it has become very much more saline due to freezing activities, and that has made the water heavier. So the water in this case will sink to the lower portions. Okay? It will sink to the lower portions. Now, where will it go? This water cannot go furthermore. It is already at higher latitudes. Where will it go? There is only one place for this water to accommodate itself. It moves towards the lower latitudes. Now, meanwhile, in the region of the lower latitude, what do we experience? That there is heating of water. Heating of water means slight expansion. When there is slight expansion of water means what? Water becomes lighter, isn't it? Overall, the water becomes very lighter. So the lighter water gains a height advantage, tends to flow. And meanwhile, the other portion of the water also becomes lighter, rises up to the surface, and then it will also end up flowing. Now, there is a vacancy created in this region from where the water is getting heated up and rising up. There is a vacancy which is created. So, this water which is coming from higher latitudes will rush in to fill that vacancy. It will rush in to fill that vacancy. And that is how eventually you achieve a complete circulation. And this circulation happens between the higher latitudes to the lower latitudes. Why? Because of difference in terms of temperature, salinity, which leads to a difference in density. So that is why, because temperature and salinity, both of them contribute to this circulation, this is what is referred to as thermohaline circulation. So here we know that the circulation is caused between the higher and the lower latitudes due to difference in temperature and salinity. Now, what this circulation is about? On the surface, water moves from lower latitudes to the higher latitudes while the opposite motion is observed subsurface. Okay. Now, this is what is referred to as thermohaline because it is dependent on temperature and salinity conditions. That is why this circulation is referred to as thermohaline. Thermohaline circulation. Okay. So that thermohaline circulation basically does what? It brings the water from, what is the purpose of this circulation overall? It brings the water from lower latitudes to higher latitudes and vice versa. So can we say that it brings about a greater mixing of water between different latitudes, thereby helping in distribution and transfer of heat from one region to another? Right? It can bring about the distribution of heat, transfer of heat. So we do know that when we talk about planet Earth is extremely heated up at a great degree at the region of the lower latitude, whereby it is experiencing a kind of a heat deficit in higher latitude. So in order to ensure that there is no heat imbalance, that heat transfer needs to take place from lower latitude to higher latitude. Generally, you have atmospheric circulation in the form of wind movement, which is able to carry this out. But when you don't have this atmospheric circulation, meanwhile, that is present. But other than this, also, this oceanic circulation ensures heat distribution and proper heat transfer. Other than that, this also helps transfer of nutrients from the lower latitude to the higher latitude and vice versa, which is very, very important for the survivability of marine species because the availability of nutrients is important for their very survival. They cannot go around fetching for exotic vegetables and fruits. Whatever the nutrients may be dominant in one particular region will have greater amount of marine population. Now that nutrient is distributed all along. So that is the twin purpose of the thermohaline circulation. First, heat distribution, and second, you have nutrient distribution. Okay, heat distribution and nutrient distribution, these are the two things that you will come across. So this is basically a schematic diagram or a schematic representation of what this thermohaline circulation basically is about. What this thermohaline circulation is about. Okay, now this is observed almost across all the oceans, and we will come across this. This is observed as a part of the ocean current movement and so on as well. Now, anybody having any doubts in this point or up till now, any doubts that you have, feel free to ask right now. After this, we will be proceeding ahead with the portion of tides and waves. So, any doubts that we have up till now, feel absolutely free to ask, regardless of what the doubt is. Even if it is of the previous module, fair enough. If you have a doubt, feel free to ask. So, by that, I can presume that we don't have any doubts. Nutrient distribution. Okay. So, what happens in the case of the ocean is that oceanic regions, you have many of the species which are basically dependent upon the availability of nutrients for their survival. Right. Now, many of the species in the oceans, they come to the categories of what are referred to as filter feeders. And when you will attend a session of environment, you will come across these term filter feeders. Now, these are basically those kind of species which are dependent on the nutrients and the small particulate matter which end up floating around in the ocean. So, The lack of availability of nutrients in a region can mean an absolute dearth of population of the species of that region. So that is why nutrient circulation is very, very important, not only within an ocean, because oceans they spread across tens of thousands of kilometers, but also in between different oceans, so that the other species also get an idea or basically an opportunity to survive. Now, that is why in this case of thermohaline circulation, when you have subsurface water which moves towards the lower latitudes, that subsurface water, along with it, brings many suspended particles to the lower latitudes. Now, when it reaches the lower latitude, it gets heated up, it rises up. So that means those particulate matter are available for the marine species in the lower latitude as well. Okay? I hope that is clear, Aarti. Amy, do salinity have any role on corals? Not significantly. If the water is very saline, then the corals won't be able to survive. Moderate salinity, they are able to survive. So if the salinity, let's say, varies between 33 to 41, generally you will find, or almost 33 to 40 or 39, corals are able to survive in that area. Uh, okay, Anshu, you have a question from the previous one. Direction of polar jet stream is west to east. Why? Direction of all the permanent jet stream, Anshu, is from west to east. And that has got to do with the dynamics of the rotation of the planet as well. Just like the same principle involved in the movement of MJO from west to east. Here also, when you have the condition of rotation of the planet, there will be a natural momentum for the winds to be moving from west to east. Having said that, there are logics which are in place that the westerlies winds, which are important along with the polar easterlies for the germination of these jet streams, that gives the direction in a particular region. But here, always understand it has got more to do with the rotation of the planet as compared to the contribution made by any individual wind. Okay. Prajwal, how freezing brings increase in salinity? Because in that region, wherever you have the freezing which is happening, that basically means removal of water in that particular region. So salt is left behind, right? And basically, you have, when salt is left behind, water remains frozen. Some amount of salt will also get frozen. But in majority, what will be frozen? Water. So greater salt will be left behind, and hence in that unit sample of water, now the salinity level will be higher, right? So freezing, evaporation, whichever factors lead to removal of water from a water sample and the salt gets left behind, all these factors lead to an increase or rise in salinity. Okay. Thermohaline circulation happens in all oceans to varying degrees, almost in all oceans except in northern Indian Ocean. In the northern Indian Ocean, you don't have any higher latitude which is present. In northern Indian Ocean, it is closed by landmass. So there you don't have a distinct thermohaline circulation happening. Pranay. And Vishal, how the water is able to move from lower latitudes to higher latitude? Is it only because of a temperature or a thermal difference? There is a thermal difference involved, but due to increased heating, the water in the lower latitude tends to expand a slight bit. And when the water tends to expand, it gains a kind of a height advantage. And that height advantage initiates a motion. So imagine in one region, water is having a greater height, in another region, water is having a lesser height. Always it will flow from a higher height to a lower height. Why it has gained a height advantage? Because of increased heating in the lower latitudes, which lowers the density. Okay. Jet streams are stronger in which hemisphere? Generally in the northern hemisphere, because the temperature difference is much more exaggerated because of the presence of increased dominance of landmass. Okay. Then Vivek, current circulation in case of thermohaline. What do we mean by that question, Vivek? Which current circulation? Are we talking about the ocean currents in this case, or are we talking about something else? So when we are talking about the circulations of thermohaline, See, the ocean currents which are in existence, they will also have some role to play. But let us first of all familiarize ourselves to what are ocean currents, which are the ones which we refer to as ocean currents. Then you will automatically gain an idea. What would be the speed of circulation? So this is a very slow circulation, Anand. This is not a very quick circulation. It will take multiple years to span through the entirety of, let's say, the Atlantic Ocean itself. So you have this kind of a thermohaline circulation which is observed across all the oceans, where water of all the oceans, they get up being mixed, and that takes place over a leisurely time period of around 1000 years. So it is a very slow circulation rate. We'll come across the global conveyor belt concept. There we will familiarize ourselves with this. Yera, at 2000 meter, how water moved to lower latitude. Okay, you are talking about this. This is the depth, right? So here, as the water gets colder, it starts to sink. Will it sink to the ocean bottom? Absolutely not, because the ocean bottom has got high salinity, right? As compared to the polar areas, the ocean bottom will always have a higher salinity. Observe in the case of the thermohaline or the halocline conditions. When we talk about higher latitudes, the salinity at the surface is around 34. At the base, it is around 35. So the salinity at the base is always going to be higher. Temperature is going to be significantly lower. So that is where the density of the lower water is always going to be higher. This is going to be very dense water. So that is why majority of this circulation happens up till a level beyond or above the lower base of the ocean water, because the lower base of the ocean water is largely fixed in terms of the temperature and salinity conditions. Okay, Shilpa, this is a specific time or is it a continuous process? It is a continuous process, my dear friend, observed across the year. That is a continuous process. Okay, so I hope we are clear. Pranay, economic conditions happening in Europe and US determined by geographical. So some contribution is made by the geographical factors, but there are other geopolitical factors, economic interests at play as well. Geopolitical factors can not be completely blamed for all the issues going around in the Western world. So now we come to the portion of tides and waves. Vishal, we measure rainfall in terms of millimeter. Generally, it is measured in terms of millimeter, but it can be it is the annual average that you will take. It is converted into centimeter for a better reading. But when it is measured in terms of millimeter. Now we come to the aspect of tides and waves. Now these are some things, or few of the things that we have been familiar with right from our childhood days. If not, we would have actually seen it somewhere, or we would have observed it, or we would have read about it somewhere. Now both of them are very different. Many of the times we end up mixing or in a way confusing between the concept of what is a tide and what is a wave, but both of them are very, very different in that instance. So, for example, waves are caused primarily due to what? Due to movement of winds. Movement of winds. Right. It is the movement of winds which is able to carry the water along with them. Now, the image that you see is not of a tide, it is of a wave. So, what is a tide? Tide is when the water goes up, higher up, and comes down twice a day almost. So water basically comes up, the level goes up, and the level goes down. So when we talk about tides, it is the vertical variation in the level of water. Vertical variation in the level of water. Water twice day. Okay, in majority of the cases, twice a day. So that is basically what is referred to as a tide. So let us take a deeper look into what these are. Let us try to understand how they are created. What is the methodology of formation? So we start with, first of all, the waves. So when we talk about waves, waves are basically a kind of an undulation which is brought about by the movement of the wind. So when the wind tends to move, it tends to drag the water along with it. It tends to drag the water along with it. But then the wind has got limited carrying capacity. It cannot carry this sample of water endlessly for hundreds of kilometers. So this water will eventually be dropped. The wind moves along, and this wind will again pick up another sample of water. It will again be picked up, again will be dropped. So that is how you have the generation of these waves. So let's suppose if we have water, let's suppose the oceanic water. On top of it, if we have the wind movement, on top of this, let's suppose we have a wind movement. Now, when we do have a wind movement, this water tends to get picked up, right? It tends to get picked up, tends to get dragged, but then eventually will be dropped. This water will sink down, right? Now, meanwhile, water from here will also get picked up. It will also get dropped down. Water from here will also get picked up. It will also get dropped down. So, like that, the water tends to return once it is dropped down, it tends to return to its original place. Okay. It tends to return to its normal and original place. So that is where, when the water is picked up, wherever the water is picked up, there will be a slight undulation in terms of the height. The height will increase in that portion as the water is picked up. But when the water falls down, there will be a kind of a syncline or a kind of a depression which is created, a trough. And again, where the next water is picked up, there will be a crest, there will be a trough. Next time, as the wind is continuously moving, the wind is continuously moving. It is not that one sample has moved, the next sample will come tonight. No, the wind is continuously in motion. So as the wind is coming in, this water will be picked up into the region of the trough, right? So this region will get converted into a kind of a trough. And as the water is being picked up and dropped here, there will be an accumulation of water here, and so on. It will continue. So this is a kind of a crest and trough kind of a formation. So where there is a crest, that is followed by a trough, and it keeps on interchanging because of the movement of the wind. Which force is responsible for its return? It is basically the natural inertia. So if you drag water, you drop it down, it will fall down and it will try to have a return. So it is not a large path of return. It is a very small area. In this small area, water will rise up, fall down. So if ever you have been to a region of a high sea, or a region, let's say, where the water is particularly deeper, you will observe that regardless of how the waves appear, like, the water will rise up here, will sink down, then again will rise up here, will sink down in this region itself. So the water does not have lot of horizontal variation in this case, right? It is in the coastal landscape where we observe a different pattern, where the water comes inwards and then drags itself backwards. But in the case of the high seas, the water will simply rise up here, will end up falling, again rising up when the wind comes in, again falling in. So generally, when we talk about the particle motion of the water, observe the particle motion of the water. So water undertakes or undergoes a rotational motion, right? The water particles, they are brought up, they are pushed down. So that is why the individual particles of water will indicate or observe a rotational oscillatory motion. That is, they will repeat that motion again and again, hence oscillatory. So the particles would indicate a rotational oscillatory motion. If that is the case, then why does it happen that in coastal areas we observe that the waves they come in and the waves they go back? We have observed, or all of us would have observed this, that the waves come in further inland and then goes back. That is what is also referred to as a swash and a backwash. So when the waves they rush in, that is what is referred to as swash. And whenever the waves come in, they also go back. They retreat, what is referred to as a backwash. So why does that swash and backwash happen? So let me write it down first of all what swash and backwash is. So when we talk about swash, incoming of waves to the coastline, and backwash. Backwash refers to the retreat of the waves to the original, or not to the original, in fact, to the sea from the land. That is backwash. Now let us try to understand why does it happen that when you have a coastline, let's suppose this is the water, here you have the coastline. So in this case, what happens? In this case, basically, you will observe that the water significantly moves forward and then retreats backward. So it is not a circular oscillatory motion here. But why? It is a kind of a translatory motion here. Why? That is because as the water approaches the coastline, the depth of water tends to increase dramatically. In the coastal areas, the depth of water basically decreases. And during the condition or during the occurrence of a wave, what is the prime factor responsible? You have the wind motion which is responsible. Now this wind will carry the water upwards, then it will be dropped here. It will return to its original position. Water will be carried, dropped, return to its original position, carried, dropped, return to its original position. Right? But what happens when you reach the shallower region? The same winds, they will be carrying the water, that water will be dropped, but here it won't be able to return to its original position because the water is not deep enough. So in that case, by the time the wind picks up the next volume of water, it will start accumulating here. Observe here, water tends to accumulate significantly. So that is why it gives you an appearance in the coastal areas when the water gets shallow, it gives you an appearance that the water is building up. Why? Because the depth is not very much, and that is why it keeps on building. And that is when the water gains a kind of a translatory motion. It moves forward because of accumulation. And as it moves forward, that is when you will observe the water to have a swash. Meanwhile, this water has been carried from here, will always have a tendency to move to its original momentum, original position. That is why the water tends to move back in the form of backwash. Okay. And how is the water carried forward? It is carried forward by the wind. So, stronger the wind, stronger will be the movement of the water. So, that is why when the winds are very strong, you have very high waves which are created. And also, the waves, the height of the waves, oftentimes will also be a product of how deep the coastal landscape is. So that is why even across India, you will come across various coastlines which have developed, which end up developing very high waves. And certain areas where it becomes suddenly very deep, there you will find that the wave height is very different. So that is basically the occurrence of wave. Yes, Pranay, that is also correct, slightly ever so, but it is also the regaining of the natural momentum and the natural inertia. Then we come to the portion of tides. How are tides generated? What do we mean by tides? So basically, every day in the oceanic water, you have an occurrence or an instance where the water level increases and then the water level goes down. It simply increases and it goes down. That is what is referred to as a tide. Now, why does that happen? So tides happen because of two reasons, two different reasons. One is centrifugal force, force of sun and moon, and then the other is, or not exactly the centrifugal force of sun and moon, but here we can write gravitational force. Gravitational force of sun and moon and centrifugal force experienced by Earth during its rotation around the sun. So that is why across the planet we come across instances where the height of the water tends to increase in all the ocean water and then it comes down. So if I give you an idea about what this is, suppose this is the land, right? Oftentimes what happens is everywhere that you come across, it is always confused in the sense that always it is mixed with the portion of the waves. So that is why most of us from our very childhood days, we have an absolute incorrect perception of what a tide is and what a wave is. So let's suppose the normal height of the water in the ocean is this. Now, during the conditions of the high tide, the water level comes up till here. And then during the low tide, water level ends up getting up till here. That is what is also referred to as the high tide line. This is also what is referred to as the low tide line. Okay, that is what is also referred to as a low tide line. And in between this is a region which is referred to as intertidal zone. This is your normal water level. Okay, so that is what we experience in the form of tidal movements in general. Okay, so here, why does that happen? Let us have a deeper understanding of that. Why and how is gravitational pull of the sun and the moon relevant, and how does it impact the water across the planet, and how is the centrifugal force going to act. So here we have the gravitational pull of the moon and the gravitational pull of the sun. Both of them are acting in what sense? So basically, this gravitational pull is not so strong to pull the planet Earth away from where it is moving. So that cannot happen. Planet Earth in itself cannot be pulled away. But the water body on the planet Earth, that is the large oceans that we have, the water body across the planet Earth, that can indicate the impact of that pull and push. For example, and here let us talk about an important concept as well. So, first of all, suppose this is the planet. Let's suppose we consider this to be surrounded by water from all sides. Let's suppose. Okay. Slightly bulged, but I think we can manage. Now, here you have the moon, let's suppose, and here you have the portion of the sun. Okay. Now, in this situation, I'm just giving you an example here. In this situation, the gravitational pull will be extended by the moon, will be subtended by the sun also, right? Now, in this case, what happens? Because of the gravitational pull, there will be a slight bulge developed here, isn't it? Now, if there's a bulge developed here in this particular portion, right? For a moment, let's forget about sun. Let's only think about the moon here. Then we will bring in the role of the sun. So, you have a tidal bulge created there, isn't it? Now, where will the water come from? If there is a bulge in this region, means the water level in this region has increased ever so slightly. Now, where will the water come from in this case? Water is not supplied in excess, that because the moon is pulling, let all of us supply more water by the taps. This water will be driven from these areas in general. From the surrounding areas, the water will be driven here, and that is what is going to lead to an accumulation, isn't it? Now that is going to lead to an accumulation, and all the meanwhile, we have to understand the fact that planet is consistently rotating in a direction west to east. Consistently. The planet is not going to stop that let moon plates part, then we will begin the rotation. Planet is consistently rotating. So as the planet is consistently rotating, can we not say that everywhere across these regions, across the planet, eventually they will experience a kind of a tidal bulge because of the gravitational pull? We can say that, right? Because the planet is consistently rotating from west to east. So as the planet is rotating, if this is the gravitational pull of the moon, this is the position of the moon, and the planet is rotating everywhere across the central portion, in this case, you will experience a kind of a bulge. So that bulge can very well be depicted on a diagram to represent somewhat like this, right? To be somewhat like this. Here also, water will be dragged from the surroundings. So, in these areas, you will develop a kind of a tidal bulge. So, what will it appear to look like? Let us finalize that. That how does it appear to look like? So, here it will develop a feature where, first of all, let us patch up the planet. So here, the water, due to the gravitational pull of the moon, that will appear to have an indication where the water will indicate a kind of a bulge, a kind of a depletion in the surrounding regions, and another bulge in the opposite side for balance, for a kind of a counterbalance. So in these two places, the water level has increased higher than normal, whereas in these two places, the water level has decreased as compared to the normal, isn't it? So this is basically, I hope this image is clear to you. I hope this image is clearly depicted to all of you. Okay. So in these two places, water level is going to be higher than normal. So you will experience a kind of a high tide. Whereas in this place, water is going to be lower than normal. So it will experience low tide. Right? So that is why, and that is how, at the same time across the planet, two places will be experiencing, or two regions will be experiencing high tide, and two other regions will be experiencing low tide as well. Same is the aspect with regards to the sun as well. The sun also subtends a gravitational pull against the planet Earth. So it will be pulling the water towards itself, leading to a variation where the opposite side will also develop a kind of a bulge to gain equilibrium. And the other surrounding regions, they will gain a deficiency. So that is why you will always have two places indicating higher level, two places indicating lower than normal level. But here, when we talk about the gravitational pull of attraction, gravitational pull of the moon is stronger when it comes to the impact of the tides. Despite the fact that the sun is very large, gravitational pull of the moon is much more dominant in the formation of the tides. And why is that? Because the moon is much closer. This is more dominant. Dominant as the moon is much closer, or has got a kind of a proximity associated. So that is why observe, when you have the moon, then basically what you will observe is that there is the buildup of water due to the attraction by the moon. There's a kind of a buildup, and this water is basically pulled up from the surrounding. This accumulation is pulled up from the surrounding. That is why this buildup is happening. So if you experience a high tide in this region, you will experience a low tide in this region. Now, moon also ends up moving around the earth. Moon and earth, they are not static. So this moon will also come eventually in this position. Now, when the moon comes in that position, means what? The condition of the arrangement or distribution of water will change. The region which had low tide will now experience a condition of high tide, and vice versa will also be true. Right? Then again, the moon will come, let's say, in this position. So again, the first condition will revert to itself. Isn't it? Then again, the moon will come to this position. So, like that, as the moon moves around, every place will experience two events of low tide and two events of high tide, right? Because of the arrangement of the water, distribution of the water, and the water redistributing itself in order to find a kind of an equilibrium. So this is the impact purely due to the gravitational attraction of both the moon as well as the sun. At the same time, moon will also subtend that gravitational pull and have an extent of effect on the water surface. At the same time, sun will also have an impact. So the bulges created by the moon, that is what is referred to as the lunar tide or the lunar bulge, and the bulges created by the sun, that is created or referred to as the solar bulge. We'll take a look at the images of each one of them separately, don't worry. So then comes the centrifugal force. What is a centrifugal force? It is a force acting away from center in simple terms. So any object, when it is moving in a kind of a rotational motion around the center, so that object will experience a movement away or a force away from center. That is what is referred to as centrifugal force. So for example, let's suppose we have a string and we have a ball attached at the end of the string. Now, if we rotate that string significantly, that ball will always have a tendency to move away from you. So that is the centrifugal force. Similarly, when we think about the sun and the earth, so we do know that the planet Earth moves around the sun in a kind of an elliptical orbit, right? It tends to move around the sun in an elliptical orbit. Let me mark here sun before you mistake it for a Saturn. So here you have the sun. Here you have the planet Earth. So it continues to move around the sun in an elliptical orbit. Now, as this rotation is happening, planet Earth will also experience a centrifugal force, isn't it? That centrifugal force will be experienced in the outward direction. That is what is the centrifugal force. Now, while this centrifugal force is nowhere as strong enough to push the planet Earth away from its rotational orbit, it is significant enough to bring about a change, a variation in terms of the water level. The land mass cannot be disturbed, but the water level can be disturbed. So that is where you will experience that the water significantly ends up getting thrown on the outwards here. Right. So centrifugal force also ends up generating a kind of a variation in terms of the water which is present. Okay. So both these are, that is the centrifugal force as well as the gravitational pull, both of them together, their resultant, that is what generates the final tidal bulge. Both of them are responsible for generation of a tidal bulge. One of them cannot be isolated as a factor. So here we will observe that two are responsible for creating two major tidal bulges. The tide generating force is considered to be the difference between the centrifugal force and the gravitational force of attraction. So here, in a simplistic manner, this is an image taken directly from NCRT. So basically, to represent it in a very simplistic manner, you will observe that the sun and the moon end up creating a tidal bulge. The centrifugal force creates the tidal bulge. Both of them combined creates a bulge, which is like this, right? So water is accumulated from here. So in these regions, the height of the water will be lower than normal in these regions. And in these regions, the height of the water will be greater than average. So this is the high tide. This will also be the high tide. This will be the low tide. And this will also be low tide. Okay. Now, depending upon the position of the sun, the moon, and the earth, we have the variation in types of tides. So we have the spring tide and the neap tide, depending upon the position of the sun and the moon. So when we talk about the position of sun and moon, here we can have a situation where the earth, sun, and the moon, they are on the same plane. That situation can always arise. Now, when they are on the same plane, let's suppose the sun is here, the moon is here, the earth is here. They are on the same plane. So the tidal bulge across this plane, observe here now. Observe, I hope you would be able to look at the image on the screen. On the screen, you would be able to observe the solar tide, a bulge created as a result of what is referred to as the solar tide. Right? And then you will come across the lunar tide. Lunar tide is much more amplified as compared to the solar tide. Why? Because the gravitational effect is more, because the moon is closer to the planet Earth as compared to the sun. So when they are on the same plane, here, what do you think happens? Both the bulges, the bulge created by the sun and the bulge created by the moon, they end up getting added, right? So in this position, what do you think the high tide will be? The high tide will be higher than the normal high tides, or will it be equivalent to the normal high tide, same as the situation before, or will it be lower than the normal high tides? What do you think? Good, Anand. Very nice. Good, Annie. Namita, Utkarsh. Correct. Shubhajit. Correct. So in this case, what will happen? High tide will be amplified, right? High tide is amplified. And what do you think about the low tide? Low tide will be as the case with the normal low tides. Will it be lower than the normal low tides? Will it be higher than the normal low tides? What do you think will be the condition of low tide here? Think about it carefully. Perfect. Very nice. Namita, Shubhajit, Shilpa. Understand this. And Ajit also. Roshan also. Very good. So in this case, understand it. So here, water from these regions are utilized to supply to this higher bulge. So that means in this region, level of water will deplete quite substantially, isn't it? So low tide is lower than normal. Now, these are the conditions which will be observed, which will be experienced when the sun, the earth, and the moon, they are on the same plane. Then you will be able to experience this, right? So whenever they are in a similar actual plane, they are on the same line, that is what is referred to as the position of syzygy. Okay, so that is a position which is referred to as syzygy. Now, even in syzygy, the moon can be in front of the planet Earth, it can be behind or the opposite. So moon and the sun can be on the same side, moon and sun can be on the opposite side. So when the moon and the sun are on the opposite side of Earth, that is what is referred to as opposition. And when they are on the same side of the planet Earth, that is referred to as conjunction. So this happens twice a month, right? Once in this position and other time in this position. It is experienced twice a month, 2 times a month, right? Every 14 days, because for the moon to move across and around the earth, it takes around 28 days. So it is in 14 days that the moon will be able to reach here. Okay. So that is basically the aspect of spring tide. This is referred to as spring tide. Namita, conjunction and opposition basically are the positions of syzygy. So when we talk about the condition or the position of syzygy, so here we have to understand that whenever the Moon and the sun, they are on the same side of planet Earth, right? That is referred to as conjunction. And moon is opposite to the sun, Earth is in between, that is referred to as opposition. Okay. Now, in both these cases, what will happen? The lunar tide and the solar tide ends up getting added. Lunar and solar tide gets added up. Now, what happens when, let's say, after 7 days, the moon will move here. Okay. From this position, the moon has moved here. Now, when the moon is, let's say, perpendicular to the plane of the earth and the sun, that is when we have a situation where, observe the lunar tide now. This is the lunar bulge. Observe the lunar bulge. And observe the solar bulge which is created. Okay. Now, in this case, the lunar bulge or the lunar tide and the solar tide, they appear to cancel each other, isn't it? So, in this situation, lunar tide and the solar tide cancel each other out. So, what do you think will be the height of the high tide? The high tide, will it be amplified? Will it be normal? Will it be lower? Very good. High tide is lower than normal. Okay. And the low tide is quite normal in this situation. So the low tide conditions of spring tide will be much lower than the low tide conditions of the other, that is the neap tide. So that is basically because the lunar tide and the solar tide, they will cancel each other out. So that is what is condition referred to as a neap tide. This is experienced when they are perpendicular to each other. And this position, when they are perpendicular to each other, that is referred to as quadrature. That position, when they are perpendicular, that is referred to as quadrature. When water attracted by the moon and created the tide, it is called the lunar tide. Yes, that is correct, Aarti. So that is what is quadrature. So when we talk about the spring tide, when the sun, the moon, and the earth are in a straight line, the height of the tide will be higher because it gets added up. They occur twice a month. So one on full moon period, another one on new moon period. So both of them, they get added up. So when they are at the same line, that is the syzygy. That position is referred to as syzygy. And syzygy can be of two types. You can have conjunction when the moon and the sun are on the same side, and you can have opposition when the moon and the sun are on the opposite. Kalyani, the bulge created by the, see here in this image, notice here carefully. This image, if you take a deep notice into this, observe, you will have a mention here of a solar tide and a lunar tide. In both these images, you will observe. Observe the second image, for example. You have the solar tide. This bulge is the solar tide. Now that means what? It is created due to the gravitational impact of the sun. And here you have the lunar tide. This bulge is referred to as the lunar tide. So what is this bulge? Created due to the position of the moon. So that is where the gravitational effect of both of them will be acting. But the gravitational effect of the moon will dominate. That is why it is basically going to have a greater bulge. Okay. Right. So that is basically the condition of a spring tide. Every 7 days, it will then revert to the condition of a neap tide. Right? So here, think about it again. So here, if the position of the moon is here, it is a spring tide. When the position of the moon comes here, it will be a neap tide, again a spring tide, again a neap tide. So every 7 days, it changes from a spring tide to a neap tide. So a 7 day interval between the spring tides and neap tides is basically observed. The sun and the moon are at right angles to each other, and the forces of the sun and the moon, they tend to counteract each other, cancel out each other. That position is what is also referred to as quadrature in general. Okay, so here, basically, if you observe, that is where you have the classification of tides based upon the position of sun and moon. Okay, now tidal motion twice a day. Okay, think about it. I'll take you back to the earlier image. So think about this condition. So here, when you talk about the position of the moon, let's say consider this image. Position of the moon is here, let's suppose. So you will have a tidal bulge here, isn't it? Right? Now, the planet rotates continuously, and continuously the planet also rotates, the moon is also moving. So different places across the planet will get the exposure to the moon within one day, within 24 hours, the entire planet will get an exposure to the moon. So let's suppose the planet is rotating like this. So as the moon is exposed here, this is the region which will be experiencing a kind of a bulge, while this is a region which will experience a low, and then again a counter bulge here. So the region which was experiencing low tide earlier now has experienced high tide. Okay. Then again, let's suppose the moon's position or the planet's position is such that the moon is exposed here. So again, it will revert to the earlier situation. The bulge will be like this. So again, this region, which was earlier low tide, then has experienced high tide while the moon was here, will again be experiencing low tide. Similarly, when the moon comes here, that then also you will have the same impact. So overall in 24 hours, different places of the planet will get exposed to the moon, right? So 24 hours time window, if you can consider, different places will get exposed to the moon. Let's assume this region A. Now in that entire 24-hour period, A has experienced low tide twice. First of all, low tide followed by a high tide. When the moon reached here, A experienced high tide. Again, when the moon reached here, A experienced low tide. Again, a high tide. So, twice it has experienced low tide, and twice it has experienced high tide within a day. So, if you divide it by 24 hours, basically that means every 6 hours, this variation changes, right? So, that is why in majority of the cases you will observe that 6 a.m. early in the morning, the water level goes down. That is a condition of low tide. Then again, after 6 hours, that is 12 p.m., the coast guards, they start telling you to vacate the beaches because the tide increases the water level. Again, after 6 hours, generally around 6 p.m. in the evening, water level again recedes quite significantly, condition of a low tide. And again, after 6 hours, that is 12 a.m. at night, you have a situation of a high tide returning again. So, this is basically how, in one particular region, you end up experiencing the conditions of high tide and low tide repeatedly. Is that understood, Anand? Right? I hope this is clear. Now, then after that, we come to the few of the characteristics. So basically, the tidal bulge, right, the increase in the height, that is oftentimes magnified, accentuated, amplified on the bottom relief feature of the coastline. For example, when the continental shelves are wide, there is a greater variation in terms of the height impact because of the features of the bottom relief. In many of the cases, the retreat of the tides from the high tide to low tide is very demarcated in the case when the continental shelf is very shallow. For example, if you consider a region like this, and let's suppose here you will have the water, right? Now, during low tide, let's not consider this region like this. Let's have a consideration like this. Now, during low tide, the water level will recede. It will come down. So, during low tide, let's suppose there is a small vertical variation. But here, you will observe that the water level has receded maybe by a few kilometers. During high tide, let's suppose there is a slight vertical variation. But here, observe the impact on the coastline. Observe the impact on the coastal area. So here, what do you observe? That between the high tide and the normal, and between the high tide and the low tide, the difference of distance has been amplified. Why? Why has the distance been amplified? Because of very simple aspect of variation in the tidal height, and the slope is very shallow. This is experienced in Odisha, in the region of Chandipur coast in Odisha. In Chandipur coast, the coastline or the coastal surface, the coastal area, the coastal land is very, very shallow. Which means what? Which means water recedes during low tide significantly for a few kilometers. And again, water ingresses by a few kilometers when you have the condition of a high tide. That is why here you will have a very unique experience where if you go during the daytime, let's suppose during the conditions when the high tide has receded, you'll find all the restaurant owners, the small shacks and shanties which are present in certain areas, they will start laying down the tables, right? And again, when the water starts coming in, all those tables are quickly packed up, they are moved to the shore, and then again the water comes in. So that is a very unique characteristic observed near Balasore in Odisha, that is the Chandipur coastline. And this is what UPSC had asked once in prelims. I think it was a prelims of 2017, that why is or which place of India experiences a wide variation in terms of the tidal movement. So that was Odisha. Now, the shape of the bays in the estuaries also end up accentuating the impact of the tide. For example, I want you after the class to locate Bay of Fundy. Locate Bay of Fundy on the atlas after the class. Now, this is the region where you will have the greatest amount of tidal variation. One of the highest tidal variations is observed here because of the shape of the coastline. Oftentimes, if you have a pinpointed shape or a narrow shape which is happening, the height eventually ends up getting accelerated, accentuated, or ends up getting decreased in the process. Okay, so that is basically the characteristic. And then we have another factor. For example, sometimes, let's suppose you have a situation where from the top view or from the side view, if you will observe, let's suppose you have a rocky area, right? and here you have the sea. Now, from the side view or from the top view, if you will observe the same region, let's suppose from the top view, this region gives you an appearance like this, a narrow inlet, and then you have the sea. So, what happens is that during the condition of a high tide, the sea level will increase, isn't it? The sea level tends to increase during the high tide. So, water will rush in. The water will rush in. Now, this rushing in of water is generated purely because of tidal movement. Hence, that is referred to as tidal current. Okay? This rushing in of water generated purely because of tidal movement. Hence, tidal current. Now, the water will get filled up in this region, let's suppose. Water gets filled up here. Now, during the condition of low tide, the sea level will go down. It will come somewhere here. So all that water will rush back out. Again, a tidal current. So oftentimes, tides are channelized between the land masses, inducing a kind of a current. Water is channelized because of the variation of tides, and that is what is referred to as tidal current. Okay? Now we move to the portion of ocean currents. But before ocean currents, we will take a break. Okay, so let's take a break and we come back and then we initiate the discussion about ocean currents. So we'll take a break for 15 minutes. And let's be back in 15 minutes and we shall continue. Okay. Yes, it is USA, but where in USA? That is something you have to observe. Which portion? See, when I ask you to locate any particular place, it is not to find it out that, okay, this is the location, then I know it. Observe the conditions of water around, observe the depth of the water around. This is something that you can observe directly by looking at the map itself. And then you will get an idea if the tide gets accentuated or not. Okay. This kind of tidal current is basically observed in various parts in the region of western coast of India. You have many of these backwaters where sometimes we experience these tidal currents in existence. Okay, tide is created by lunar. No, it is created by the impact of sun and the moon. Okay, lunar. It might be meaning lunar rather than lunar. Okay, right. So let's take a break and let's be back in around 15 minutes of time. A confirmation about the audio, please, guys. If the audio is clear and available. Thank you. So, Abhinav, you had asked a question about the tidal currents. Tidal currents are basically the sudden movement of water initiated due to the movement or the horizontal variation in terms of height, which is initiated by a tide. So many of the times when you have a channelization of water, let's say in a region across the coastline where there is an indention or where there is a kind of a region where water can rush in, so that rushing in and rushing out of water is initiated due to the tidal variation. That is what is referred to as tidal current in general. Okay, now we come across what is referred to as an ocean current. So the oceanic waters overall, even though when you take a look at it, the ocean waters appear to be absolutely calm and featureless. But in reality, that is not the case. These oceanic waters, they are consistently in motion. And near the surface, they will be consistently moving in one direction, right? Any kind of a direction, but there will be a kind of a motion where you will have large volumes of water moving from point A to point B continuously, okay, with a certain kind of velocity. It will be like almost akin to a river moving in the ocean itself. That is what is referred to as an ocean current. So, if we have to think about ocean current and the features of ocean current, what do we designate or what do we refer to an ocean current? Here, basically, it will have a kind of a regular and constant movement of water in a set direction. Okay, regular and consistent motion of water in a set direction. And here, the water will be moving in a kind of a direction in a particular speed. The water will have a tendency of a speed as well. Many of the times, millions of gallons of water are moving every hour, depending upon the strength of this ocean current. Now, this ocean current is driven by many different forces. We'll take a look at all these forces, the classification of the ocean currents also. Okay, so here, this ocean current, by the way, it is not a phenomena which we know of only today or let's say only in the past few decades. This has been known to us for many centuries. In fact, the ancient or in the Middle Ages, the sailors and the mariners, they would plan their journey owing to the direction that the oceanic water would be moving into. So you had the Portuguese sailors and explorers who were basically very well aware about the movement of the oceanic water, and that is how it spread, the information about it spread across the entirety of the world, that oceanic water has got a kind of a definite direction and a definite motion induced in it. So let us understand what these ocean currents are, what their classification is, and the forces which end up inducing these ocean currents. So we start first of all that they are like river flow in oceans, right? River flow means a kind of a set directionality of movement, a kind of a unified motion observed in oceanic water. So regular volume of water in a definite path and direction, inducing a continuous movement. Continuous movement. That is what is referred to as an ocean current. Now, this ocean current is actually influenced by various different forces. They are classified as primary forces, which in first of all initiate the motion of the water itself, and then you also have the presence of secondary forces, which basically end up shaping the movement of water, that whether it will move from right to left, left to right, and so on. Now, when the water moves in a set direction, depending upon the speed, that motion is classified into a stream, current, or sometimes even a drift. Now, drift, when you hear about the term drift, it refers to very slow motion. Drift refers to a kind of a very slow motion which is initiated. A stream is particularly fast, and current is also fast enough but oftentimes does not carry as much amount of water as a stream can eventually carry. So here, when we take a look at these forces, first of all, why is it that these ocean currents are induced? Why is it that these ocean currents are in existence? So basically, first factor, major factor, is the heating by the solar energy. So what happens? Across the planet, the solar insolation is significantly to the maximum in the lower latitudes. So in the lower latitudes, when you have the solar insolation, which is quite significant, what happens? Water heats up. When water heats up, it gains or it basically expands. And due to expansion of water in the lower latitude, the water tends to gain a kind of a height advantage, in the sense that in the lower latitudes you will experience that the water, let's say, has got a height of more than 8 to 10 centimeters as compared to the region of the middle and the higher latitudes. So here, that creates a height gradient. So heating by solar energy, it causes the water to expand, and when the water expands, it results in about 8 to 10 centimeter of a higher water level. That induces a height gradient. When it comes to fluids or water, they will always move from a higher height to a lower height. So always you will come across the situation that this expansion induces a 8 centimeter to 10 centimeter higher level at equator compared to the middle latitudes. So you will have a kind of a height gradient. So naturally, under normal conditions, water will initiate a motion. But then motion in which direction? Motion uniformly, or is it influenced by the winds also? So there is a major role played by the winds. So the winds, it causes that expanded water to move in a certain direction. So the winds, they provide directionality to the water flow, provide a direction to the flow of water. Okay, they end up providing a direction to the flow of water. Because let's say water has expanded ever so slightly, but in which direction will it flow? Influenced by the wind. And the very easy example of this, if I can take you back a few slides, let's suppose we talk about the conditions of salinity here. So, yeah, or temperature rather. Temperature will be a better depiction of this. So, here observe. Observe that in the lower latitudes, that is around the region of equator, you will observe that the water is significantly heated. So, in the lower latitude, water will be expanded. But observe a minute thing or a minor factor in this situation. Observe that the water in this region of central Atlantic, this indicates a kind of a flow pattern. somewhat like this. Now, why do you think that is the case? That is because the winds, in this case, the trade winds, very good, Pranay. The trade winds, they are pushing the water from east to west. That is why the water is accumulating there. Here also in the region of the Pacific, observe the trade winds, they are pushing the water towards the western direction. So all that warm water gets accumulated here. So it is not only the expansion, the directionality is further accentuated, is further provided by the movement of the wind. So movement of winds are a very important factor when it comes to the direction of the water or the direction of the ocean currents. Then you have the impact of the Coriolis force. Now, when we say Coriolis force, any object which moves independently to the surface, that object will bend to the right in the northern hemisphere and will bend to the left in the southern hemisphere. So the same case is applicable in the case of oceanic waters also. So if, let's say, you consider an oceanic water or an oceanic circulation, let's suppose we consider this to be the equator, right? Now let's suppose water in the northern hemisphere, that initiates a kind of a motion. Water moves here. Now this water will have a tendency to bend to the right. This will again have a tendency to bend to the right. Again, it will have tendency to bend to the right. Again, it will have a tendency to bend to the right. Right? And in the case of the southern hemisphere, if let's say the water is moving like this, it will have a tendency to bend to the left. Here also it will have a tendency to bend to the left, tendency to bend to the left. So what do you experience here? You experience a kind of a circulation of water. In very larger areas, there is a circulation, but a circulation nonetheless. Why? Because of the Coriolis force. That is why across the Atlantic and the Pacific, in the case of the northern hemisphere, you will come across a kind of a anti or a clockwise circulation. Clockwise circulation. Whereas in the southern hemisphere, for all the oceans, so this is only observed in the case of Atlantic and Pacific, not in the case of northern Indian Ocean. Here, anti-clockwise circulation, to be observed in the case of Atlantic, Indian, and Pacific Ocean. Okay, so that is where you have the impact of the Coriolis force playing out. But here you would not observe the mention of Indian Ocean. Why? Because Indian Ocean is closed from the top. It is closed from the northern end. Atlantic and Pacific Ocean, they open up to the higher latitudes in the case of the northern hemisphere. But in the case of the Indian Ocean, you have the Indian subcontinent and the land masses of Asia, which close the top of the Indian Ocean. That is why in the case of Indian Ocean, the influence is much greater of the wind. So the wind influence is very influential in North Indian Ocean, as it is surrounded by land, surrounded by land. And in the case of northern Indian Ocean, that is the region of Arabian Sea and Bay of Bengal, what do we observe? We will observe that in the case of the northern Indian Ocean, the wind direction changes in between the various seasons. So, in the northern Indian Ocean, as the wind direction changes in between the seasons, it will have a differential impact on the oceanic movement as well. We'll take a look at it with the help of the image as well. So, reversal of winds between the seasons induces a reversal of current in northern Indian Ocean. As of now, just hold on for a few moments. For any of us who are unable to imagine this, when we come to the Indian Ocean, you will understand this. But let me show you the part with the help of the image as well, if I can. So observe in this case only the northern Indian Ocean. This is the case of the Indian Ocean. In the northern Indian Ocean, if you will observe here, this is the equator. Now, during this time of, or let's say we consider different months of the year, right? Let's assume different months of the year. Let's assume this being the month of southwest monsoon or the month of June, and this being the month of December. Now, in the month of June, what is the direction of wind motion? Direction of wind motion is southwest to northeast, isn't it? That is the direction of the wind motion. So observe the wind or observe the oceanic motion also. The oceanic motion is very much at par with it. Now, during the month of December, when you have the northeast monsoon in existence, here the wind direction is completely reversed. So look at the direction of the ocean water. It has completely reversed, isn't it? So with the reversal of the wind, because the northern Indian Ocean is closed from the northern side, that is why it has got a significant impact due to wind. Okay, but if you take a case of the Pacific Ocean, it is open in the north. If you take the case of the Atlantic Ocean, it is open in the north. But if you observe the Indian Ocean, it is not open from the north, it is closed from the north. So that is why in the case of North Indian Ocean, northern Indian Ocean, impact of wind is highly exaggerated. Impact of wind is highly exaggerated. Aarti, now is it clear or do we still have some doubt? Abhinav, what happens at equator? At equator, we'll come to it. You have the prime dominance of the trade winds. So the trade winds, they move in a general direction from east to west. So all the waters around the region will be carried from eastern part to the western part, and then you will have a modification depending upon the other forces. Okay. Okay. See, I'm not able to understand whether it is clear or not. No, sir. Clear. Is it clear or is it not clear? Please let me know. And okay, good. And Vivek, Pacific in both. What is Pacific in both? Where do you mean Pacific in both? Is it in this situation that you are referring to Pacific in both? So Pacific Ocean is present in southern hemisphere also. Pacific Ocean is present in northern hemisphere also. So in the northern hemisphere of the Pacific, or the Pacific Ocean, which is the part of the northern hemisphere, you will find or you will come across a circulation which is clockwise in direction due to the Coriolis force. Everything will appear to bend to the right. And in the southern hemisphere, it will appear to bend to the left. So you will have a kind of an anti-clockwise circulation, both in the case of Atlantic and Pacific. But in the case of Indian Ocean, the impact of Coriolis force is not so significantly higher as is the impact of the wind movement. Is that understood, Vivek? Or is there a doubt? Clear? Okay. So now we move to the other forces. Any doubts that you have till now, feel free to ask. Now we come to the other forces which are responsible. The shape of the coastline. Now, what is the shape of a particular coastline? That also ends up depicting, or that also ends up influencing the motion of the oceanic water. So when we talk about the shape of the coastline, let's suppose here you observe in this region. Let me use a different coloration. So here, let's assume that this is the region which depicts the equator. Let's suppose this is a region which depicts equator. Now here, if let's suppose the ocean currents, they are moving like this, or before that, let's suppose the ocean currents are moving due to the trade winds from a direction of east to west. Now, when they are going to hit the South American coastline, what will happen? Will they start climbing over South America? No, they will be deviated as per the shape of the coastline. So, because the shape of the coastline is such, if you will observe here, that water will end up getting deviated overall, isn't it? Now, here, this ocean current encounters the Bahamas, the West Indies, the Caribbean islands in general. Now, when it encounters this, it will get bifurcated. One part will move to the south of the islands, the other part will be moving from north of the islands. So that is where one part will move to the south of the islands, the other part moving from the north of the islands. There is a kind of an indentation in the coastline due to the presence of Gulf of Mexico. So here, water will get into Gulf of Mexico, will exit here. And here again, observe the movement of the water, initiated both by the shape of the coastline as well as the Coriolis force. So shape of the coastline oftentimes ends up depicting where the water will end up flowing. Similarly, here you have the ocean current which is moving towards northern part of Europe. Now it encounters various different types of islands and various different parts of the coastline which has got different shape. So here also, some part of the water will go here, form the Norwegian current. Some part of the water will come from here. Some part of the water might even enter into the region of the Mediterranean Sea. Some part of the water goes near the region of Iceland. So it is because of the shape of the coastline, isn't it? So shape of the coastline is particularly influential in providing the direction, right? Provides direction. Direction of flow for the ocean currents. Okay? Now, also, you have another minor factor, secondary force, which is at play, and that is the role of ocean bottom relief. Bottom relief features. So, ocean bottom relief, when we talk about, so that basically means that what is present at the ocean bottom. Now, generally, across the oceans, one very consistent bottom relief is what? The mid-oceanic ridge. isn't it? Mid-oceanic ridge is one of those prominent bottom relief features. So here you have the mid-oceanic ridge, or the in general the role played by mid-oceanic ridges. Now in this situation, what do you come across? You come across the fact that when you have, let's suppose, water which encounters or interacts with the mid-oceanic ridge, so here the water will get divided. Oftentimes the flow will be interrupted. So for example, if we take the case of the North Atlantic, in the North Atlantic you have the presence of the North Atlantic or the Mid Atlantic ridge. Mid Atlantic ridge extends all the way from here. So in this position of North Atlantic ridge, here you have the Wyville-Thomson ridge, the underwater bottom relief. This is Wyville-Thomson ridge, or let me write it down here. In the region of North Atlantic, we have Wyville-Thomson ridge. Now this Wyville-Thomson ridge, now the ocean current which is coming up till here, when they encounter that kind of an obstruction underwater, now these ridges, they are not minute in proportion. They also have significant amount of a height. Many of the times it is similar to a kind of a hill that you find on the ground level. So here when the water encounters this Wyville-Thomson ridge, due to the obstruction offered, the water tends to bifurcate or trifurcate in various different paths. So here what you come across is that this part of the ocean current, which is also referred to as the North Atlantic drift. So North Atlantic drift, Atlantic drift trifurcates. Trifurcates means divided into three parts. Trifurcates as it encounters the obstruction in the form of the mid-ocean ridge. So that is again a kind of a minor force, a minor secondary role played by the ocean bottom feature. Not everywhere will that be very prominent. In some places, for example, in the North Atlantic, this is something which is experienced. This is something which is prominent enough. So that is what we have as the forces which end up influencing the ocean currents in general. Now, after this, let us take a look at the characteristics and the classification of the ocean currents. Now, primarily, we have already seen that all the factors of solar insolation, evaporation, precipitation, etc., that is restricted to the top portion near the surface of the ocean water. So even the expansion of water which is happening due to increased amount of heating, that expansion of water will be restricted to the top portion near the surface only, isn't it? The influence of the wind also will be very much present near the top surface. So when we consider the oceanic water, let's suppose, now it has got depth as well. Now here, when you will observe a wind motion, the wind will drag the water, It will generate a kind of an ocean current with the help of the dragging of the water in general. So here, the movement of the water will be maximum closest to the surface. Now that water will end up dragging the water to the slightly lower level. That will end up dragging the water to the slightly lower level. That will end up dragging the water to a slightly lower level. So in a way, you will observe that the wind is dragging the surface to the maximum. And that impact keeps on reducing as you go to the depth. So overall, the ocean currents are strongest near the surface. And near the surface, they might very well end up attaining a speed close to around 5 knots. But as we go into the depth, the currents are generally slow with speeds less than 0.5 knots. So the speed reduces as we move from surface to the depth, right? Knots is basically a unit of speed which is uh, referred to, or which is generally applied whenever you have navigation services in maritime areas, or ship movement, or even airplane movement. All of that is covered by a unit, knot. What is 1 knot in terms of kilometer per hour? Let me see if we are aware of this or not. What is the conversion of 1 knot in terms of kilometer per hour? Any of us who is aware of it? Very close, Pranay. It is basically around 1.8 kilometer per hour. When we talk about knot, so 1 knot represents around 1.8 kilometer per hour generally. Okay. Then the other characteristic or the classification of the ocean current, you'll find that you have a general classification based on the depth of the ocean current, at which depth you have the presence of ocean current. So at the surface, you have majority of all the ocean currents that we are going to study, that is going to be surface current. Now all that surface current, that constitutes only 10% of the water. Only the 10%. That is up till a depth of 400 meters from the surface only, not beyond that. So all the oceanic currents that we are going to study, we are going to study about the surface currents, because that is restricted to the surface. So only a minor portion of the oceanic water, only a minor portion of the oceanic water, that is influenced by the surface currents. But a major portion of the oceanic water is influenced by what is referred to as deep water currents. That is in the deeper portion. So here they move around the ocean bottoms at the depth, and this is what is also responsible for large scale temperature distribution and nutrient distribution. So this is carried out due to variations in density influenced by temperature and salinity. Motion is influenced by temperature and salinity. Okay? That is another major factor that you will come across. Then after that, we have a classification of ocean current depending upon the temperature as well. So you have the classification as cold current and the warm current. Now, here, let us understand something very significant, which will help us not have any doubts when we talk about few of the cold currents and few of the warm currents. Cold currents, just like in the case of cold advection. When we were talking about wind movement, we talked about cold advection and warm advection. Cold advection would be what? Movement of colder winds into the warmer areas. Warm advection would be movement of warmer winds into the colder areas, right? So when we have a cold current, that brings cold water into warm water areas. Generally, it is observed when you have water moving from higher latitudes to the lower latitudes, they are generally regarded as cold currents. Now, please understand, you don't have a particular delineation that or an absolute factor that if the temperature of the water is, let's say, below 15 degrees Celsius, only then it will be a cold current, otherwise a warm current. You don't have any such factor. So any current can have the capacity to become a cold or a warm current depending upon in which latitude it is moving. So for example, let us understand this with the help of an example. Suppose we consider the planet Earth, and here let us suppose we consider the equator. Now, in this region, as the water is moving in, okay, let's assume it is moving somewhere around 30-40 degree north latitude. Now, the temperature of this water, let us assume the temperature of this water is 20 degrees Celsius. Now, we know that the temperature of water in the lower latitudes, this is generally around 24 to 25 degrees Celsius. Temperature of water in higher latitudes can be significantly lower. Let's say it is around 10 degrees Celsius or 12 degrees Celsius. Now, the same ocean current of 20 degrees Celsius, if it moves into the higher latitude, will it be regarded as a cold current or a warm current? What do we think? If it is moved into the higher latitude, will it be regarded as a cold current or a warm? Why cold current, Vivek? Let me know. Perfect. So here, this water of 20 degrees Celsius is moving into the region where the temperature is 10 degrees Celsius, right? So where the existent temperature is already 10 degrees Celsius, and here you have a water of basically 20 degrees Celsius which is coming there. So this will, as may all of you have given the correct answer in this case, so this is what will be regarded as a warm current. And the same water of 20 degrees Celsius, when it comes to, let's say, the lower latitude, will it be regarded as a warm current or a cold current? What do we think? Perfect. Good. Pranay, Aarti, Namita, Dhara, this time Vivek also. All of you, Yera, Roshni, Nitin, correct? So here, this will be regarded as a cold current. Why? Because it is bringing water to a warmer region. That is why it is regarded as a cold current. Okay. So that is basically what it indicates to us is that the same water temperature can end up behaving as a warm current, can end up behaving as a cold current, depending upon the temperature of the area where it is moving into. So that is why when we talk about cold currents in general, they will bring water from higher latitudes to lower latitudes. They will end up bringing water from higher latitudes to lower latitudes in general. That is a characteristic of cold current. Now, you will also find a kind of a generalization that these general cold currents are generally to be found on the west coast of the continents in the low and middle latitude. West coast of continents. Why do you think that would be the case? So this is also a feature, and we'll take a look at the various oceans and we will reconfirm this fact. So basically, let us assume that you have a continental landmass. Let's assume you have a continental landmass. Now, in that continental landmass here, in the lower and middle latitude, what will be the wind permanent planetary wind which will be in motion in lower and middle latitude. In the case of a continental or anywhere in lower and middle latitude, what will be the permanent wind in motion? Okay, lower latitude I'm talking about. Very good, Aarti. So in the lower latitude, we will have the prevalence of trade winds, isn't it? You will have the prevalence of trade winds. Now, when you have the presence of these trade winds, basically, what does this mean? If here you have the trade winds on the west coast of the continent, what will be the sea surface temperature? On the west coast of continent, they cause upwelling. Very good. So cause upwelling on west coast. And when you have upwelling on west coast, what will it do? Reduces sea surface temperature. So the ocean current that you will find across the west coast of the continents, that will be generally a cold current because of the factor of upwelling. Okay. And in the east coast, in the same region, you will experience what? Downwelling. And downwelling means warmer water will be present here. So that is why across the eastern coastline of the continents, because of downwelling, generally you will come across warm currents. So when we talk about warm currents, these are the ocean warm currents, basically are the warmer waters which are brought into the colder regions of the planet. So that is what is regarded as a warm current. So these bring basically waters from lower latitude to higher latitude. From lower latitude to a higher latitude. Okay, they will end up bringing water from lower latitude to higher latitude. So that is where you will observe that in those regions, a slight amount of warming is provided by these waters. Now, here it is usually observed in the eastern coast of the continents and the oceans. Why? Because here the presence of the winds in the lower latitudes, wind movement, causes accumulation of warmer waters in the eastern coastline, causing downwelling. And when you have downwelling which is caused, that brings in presence of warm currents. Now again, I would like to reiterate one basic fact before we move into separate oceans and the ocean currents of each of the oceans individually. One basic factor which needs to be noted and appreciated here is the fact that it is not dependent on the absolute temperature. It is always dependent on the relative temperature. If the ocean current's temperature is higher than the surrounding water, warm current. If the ocean current's temperature is lower than the surrounding water, it is a cold current. So before designating a current as a warm or a cold, always think about what is the surrounding temperature. And also keep in mind whether the water is being carried out from lower latitude to higher latitude or higher latitude to lower latitude. Generally, when water is carried from higher to lower latitude, it will be colder in nature because it will bring colder waters from higher latitude. Okay, so the designation as a warm or a cold ocean current is dependent on the surrounding water temperature quite significantly. So, designation as a cold or warm current is dependent on the surrounding water temperature. Okay, if current is colder than the surrounding water, it is a cold current. And also the vice versa will be true. Okay, so that is basically the aspect of classification. Now we come across each of these individual oceans and let us understand how the ocean currents are generated and which are the ocean currents in existence. Ideally, always advisable to understand this with the help of the Atlantic Ocean, because Atlantic Ocean in many of the cases experiences all the forces that we have been talking about in adequate proportion, be it solar insolation, be it the shape of the coastline, anything that you consider, Atlantic Ocean represents that. So that is why always advisable to first of all study, let's say, the North Atlantic, then the South Atlantic, North Pacific, South Pacific will be resembling that. So the same template, if you understand this portion of Atlantic, Pacific observes the exact same template. There is this exact same template even in the Southern Indian Ocean. The only variation that you will experience is in the case of Northern Indian Ocean. And that variation we have already seen. That is because of the reversal of the wind direction. That how, when you have the reversal of the wind, it can influence the ocean current also. So here, let us start first of all by the Atlantic Ocean. Okay. Now, one by one, we will be addressing each one of them. Now, I want you to be observant enough because in the additional reading materials, you will get the written text that oftentimes we are after, that we need a written text for this. So in the additional reading materials, you will get the written text about the ocean current. So here, advisable to pay attention and keen attention to what happens in this case. So it all starts around the region of equator. Around the region of equator, you have the piling up of water or slight expansion of water, right? So expansion of water happens, why? Because of significant amount of heating. So it leads to expansion, water gets expanded, right? Now let me write it down point by point so that it is easier for you to recollect. First of all, at equator, water expands due to heating. Water ends up expanding due to heating. Now, when the water expands, then after that, what will happen? That water is basically dragged by the trade winds. Now, around the region of equator, what is the direction that the trade winds have? The trade winds generally will be moving in this direction, isn't it? East to west. So here, the trade winds or simply the trades drag the water to the west. Okay. Now, after that, what happens is that it hits the South American coastline, the eastern part of South American coastline. Now, there it gets influenced by the shape of the coastline. Look at the shape of the coastline. It will get influenced by the shape of the coastline. So, water accumulates here, deflected by the shape of the coastline. Right? So, in the northern hemisphere, it will be deflected to the north. In the southern hemisphere, because of the shape, it will be deflected to the south. However, some amount of accumulated water will generate a flow back to form what is the counter equatorial current. So, let us understand this. So, basically, water deviates to north and south after hitting the South American coastline. Now, here, some part of the accumulated water here, some part of the accumulated water in this region begins a flow back. Some accumulated water begins a flow back. And that is referred to as counter equatorial current. Counter equatorial current. Okay. Now, let us consider the region of North Atlantic first of all. Then we'll come to the portion of South Atlantic. So, in the case of the North Atlantic, as this water starts deviating to the north, here, as it starts deviating to the north, then it is aided by the shape of the coastline here. Coriolis force will also start acting as it starts moving to the north. It hits or it encounters the Caribbean islands. And that is where, or the Antilles set of islands as it is referred to, there it is bifurcated. One part moves to the north, other part moves to the south of these Caribbean islands. Water also then from the region of the Caribbean island to the south of it, it enters the Gulf of Florida. Right? And you have one portion of the ocean current which will move from the northern portion of the Caribbean islands. Right? Now, after moving through the region of Gulf of Mexico, basically, around the state of Florida in United States, after moving through Gulf of Mexico, it comes around from the state of Florida. This is the state of Florida of United States, and that is where it is referred to as Florida current. It comes out, it meets with the portion of the ocean current which had been coming from the northern part. And that is where you have the generation of the very powerful Gulf Stream. It is not Gulf of Florida, it is Gulf of Mexico. Okay? It is the Florida Peninsula. So it is Gulf of Mexico, Utkarsh. A clarification here. So basically, the current coming out of the Gulf of Mexico, here it will come out near the region, the state of Florida in United States. Now, as it comes out, it then meets and basically mixes with the water coming from the northern part of Caribbean islands. So together, the volume of water will be very high. It will be hotter as well because this water is getting heated up continuously. So that is where together it generates the very hot and the very warm Gulf Stream. Right? It will generate the Gulf Stream. Now, that Gulf Stream aided by the shape of the coastline, aided by the Coriolis force, it will have a continuous bending to the right. And this Gulf Stream will also end up encountering a cold ocean current coming from higher latitudes, aided by the shape of the coastline around the region of Labrador Sea to the north. And that is what is referred to as Labrador Current. So, here in the region of Newfoundland, that is the northeastern coast of Canada and North America, here you will have the mixture of the cold and warm current. Whenever cold and warm currents they will meet, that will significantly augment the oxygen supply in water. That will end up increasing the phytoplankton population and overall will end up increasing the fish population. So whenever warm and cold ocean currents will meet, that forms a very good fishing ground. So this forms a very ideal fishing ground. Very ideal fishing ground. Wherever, whenever you come across a situation where a warm current is meeting a cold current, it will form an ideal fishing ground. Now, still, some portion of the Gulf Stream will be slightly cooler, but it will not lose temperature quite significantly because Gulf Stream is carrying a lot of water. It is one of the most powerful warm water currents that you will find across the oceans of the world. And this Gulf Stream, you will observe, then starts to drift to the west or drift to the direction of west to east. Right? It starts drifting from the direction of west to east. Now, why does that drift happen? Drift basically is a slow movement. Why do you think that drift happens? Very good. Beautiful, Pranay. So, there you have a multiple role played by many different objects, many different forces. One is obviously the role of Coriolis force, which will bend it to the right. The other is the role played by westerlies. In this portion of the planet, you will have the prevalence of westerlies. So, as the westerlies are moving, these westerlies will end up carrying these currents to the eastern part by the influence of westerlies. Now, here, this is what is referred to as the North Atlantic Drift. Now, it is a warm current. Even though the temperature, let's suppose, would be 15, 16, or 20 degrees Celsius, it would be a warm current. Why? Because the surrounding water temperature is very low. We are in higher latitudes now. So the surrounding water temperature is very low. So this North Atlantic drift, that is comparatively warmer, right? This is not close to equatorial region, my dear friend. If you observe where this west wind drift is, so in this image, maybe you are losing that context. So where do you think you have the Tropic of Cancer? If I have to draw the Tropic of Cancer for you, in this case, Tropic of Cancer will be somewhere here. So above the Tropic of Cancer, you can always have the westerlies in existence, isn't it? So if I take you back to a certain set of images, this is the Tropic of Cancer. This is the Tropic of Cancer here. This is the region where the Gulf Stream eventually materializes into North Atlantic Drift. So here, above Tropic of Cancer, don't we have the westerlies? I hope that is clear, right? So here, basically, that is how you have the formation of the North Atlantic Drift. North Atlantic Drift is warmer as compared to the surrounding because warm water is carried all the way from the region of the Gulf Stream, which is very, very powerful. Now, it is because of this fact that the North Atlantic Drift is comparatively warmer that you will find that the regions in Northern Europe, in the regions of Northern Europe, they tend to remain ice free for majority of the year because you have warmer waters coming from North Atlantic drift. And also the water bodies, they end up remaining available for navigation because of the warmer waters brought by North Atlantic. And this North Atlantic drift, basically, it starts to divide on the shape, on the basis of the shape of the coastline, and also on the basis of the bottom relief feature. One part of this North Atlantic drift will enter into the region of the Scandinavian nations, forming the Norwegian current. One part will enter into the region of the North Sea. One part will enter into the region here, Bay of Biscay. One part will even further penetrate into the region of Mediterranean Sea, right? But you have the Coriolis force and the shape of the coastline again, which will be at play. So here, what do you observe? Due to the Coriolis force, it will exhibit a rightward bend here. Observe the marker on your screen. So it will observe a rightward bend due to Coriolis force. And now you have water moving from higher latitude to a lower latitude. So even if the temperature, let's say, is 20 degrees Celsius, 15 degrees Celsius, whatever, but the temperature at lower latitudes is around 24, 25 degrees Celsius. So this will serve as a cold current, the Canary current. After the Canary Islands, which are situated here, that is how you have the cold Canary current. It again feeds back to the North Equatorial current, and you have the entire circulation. Is that understood? Or are we having a doubt in this? Let me know. Any doubts that prevail in this area, or is it completely understood? Okay. So by that, I gather that it has been understood. No doubts in this? Is it clear? Good. Very good. So once again, I will repeat the entire process so that it cements in your mind and so that you become more sure about it. So listen to this portion carefully once more. So it all starts at the region around equator when the water starts to bulge because of insolation. But after that, that water is carried away from a direction of east to west. Why? Because of the influence of the trade winds. Now, these trade winds will carry the water, they will hit the kind of the shape of the coastline, they will hit the eastern part of the coastline of South America. Now, when they will hit the eastern coastline of South America, that is where the water which has been carried, that will get bifurcated. One part owing to the shape, look at the shape here. So one part will be deviated to the north, other part will be deviated to the south. The part which has been deviated to the north, and meanwhile some accumulated water which is left behind in the region of Western Atlantic, that will generate a flow back, what is referred to as the counter equatorial current. Now here, the northern part, the north equatorial current, it will move. It will encounter the Antilles group of islands or the Caribbean group of islands. And there, when it encounters these islands, it will get bifurcated or divided into two parts. One will move from the northern part of the Antilles Islands, Antilles current it is referred to, other to the south portion of the Caribbean islands. Now, the portion moving from the south, it will enter into the region of Gulf of Mexico. When it moves through the region of Gulf of Mexico, obviously it will get warmed in that enclosed area. It exits around the region of the state of Florida, and that is why it is referred to as Florida current after that. After that, it mixes with the Antilles current, which has been coming from the north portion of these islands. And together, they form one of the warmest ocean currents, that is the Gulf Stream. Why it is referred to as the Gulf Stream? Because it is thought that this particular Gulf Stream has been supplied with water coming from Gulf of Mexico, hence the name Gulf Stream. This Gulf Stream carries humongous amount of water at very high speeds. And this Gulf Stream, when it moves significantly to the northern part, that is where around the region of Newfoundland on the coastal area or on the northeastern coastline of North America, that is where this Gulf Stream encounters the cold current coming from north, that is the Labrador current. That is why this is a region which is referred to as an ideal fishing ground. Okay, wherever warm and cold ocean currents will meet, that is an ideal fishing ground. So that is, after that, still the Gulf Stream retains some amount of warmth because it is a very humongous warm current. It maintains that warm portion. It continues to move west, or from west to east it continues to drift under the influence of westerlies. So here it will experience the influence of westerlies. That is why it is referred to as a drift here, because the speed is not that high anymore. The speed has been reduced. So that is where this drift then encounters these islands, right? And these drift, which is the North Atlantic drift, this is a warm current. It moves into the Scandinavian region as Norwegian current. You have various classification as Irminger current, Renel current. All these are parts of the North Atlantic drift, but not required for your general studies. So why to bother from that? So basically, this North Atlantic drift, depending upon the shape of the coastline and the bottom relief, one part goes near Iceland, one part goes to Bay of Biscay, one part goes in the North Sea, one part goes in the from the Strait of Gibraltar into the Mediterranean Sea. You have multiple different bifurcations and divisions. After this, Coriolis force is always active. The shape of coastline is always perpetually present. So these currents, they will deviate to the right again. And when they will be deviating to the right, then they will form the very cold Canary current. Why it is a cold Canary current? Because it is bringing water from a higher latitude to a lower latitude in a region where the ocean temperature might be already around 24-25 degrees Celsius. If you have, let's say, a 20 degrees Celsius water coming in, it will be a cold current. So that is how the entire North Atlantic circulation is resulted. Then if we take a look at the South Atlantic, a very similar process. So again, start with the region of equator. Around the region of equator, as there is a slight bulge in the water level, that water is dragged to the west. Why? Because of trade winds. Now, all that water in the northern hemisphere, it has moved slightly to the north. In the southern hemisphere, some part will move to the south owing to the shape. Now, accumulated water which is present here, what will the accumulated water do? Influenced by the rotation of the planet, etc., that will initiate a kind of a flow back, right? So that is what you have as the counter equatorial current generated. Now, meanwhile, here you will observe that there is a bending to the left under the influence of Coriolis force in the southern hemisphere. So this is the warm Brazil current. Okay. And then all across the planet in the southern hemisphere, in the region of Southern Ocean, you have a circumpolar circulation, which is referred to as west wind drift. Which wind do you think will be responsible for this west wind drift? What do you think? Which wind will be responsible for this? It will be westerlies here also. Very good. So westerlies are responsible for the deviation. So all across the planet, even in the case of Pacific, you will observe this west wind drift. Even in the case of Indian Ocean, you will observe this west wind drift. So that means across all the oceans, you will observe this west wind drift. Now, this west wind drift has got some part of it near the Falkland Islands, which will deviate to the left because we are in southern hemisphere. It is a very weak current, that is the Falkland current. Meanwhile, this Brazil current will mix here. And then here, as it is moving, it is a cold current in the southern hemisphere, very close to the poles. It will again deviate to the left. Now you have colder waters being brought from the higher latitude to the lower latitude. So that will be the cold Venezuela current. And that will again feed on to the south equatorial current. Okay, so that is how the circulation pans out in the region of South Atlantic. Okay? Any doubts? Why does counter equatorial current move backward? Because there is a bulge here. So bulge is created here as the water is dragged to the west. So that bulge initiates a kind of a flow back, because eventually the water will try to regain its natural position. So that bulge will gain a flow back, and hence counter equatorial current is generated. North Atlantic drift will increase salinity in northern oceans. Yes, in North Atlantic, the salinity conditions are increased significantly by the North Atlantic drift. Why? Because this brings warmer waters in the region of North Atlantic. And when warmer waters are brought in the otherwise colder areas, suddenly evaporation rate increases in those areas. And that is why salinity tends to increase in those areas. Okay? So I hope that is understood. So now we have covered the basic of ocean current. Now we take a break, the lunch break. So after the lunch break, we will cover the remaining portion of the Pacific Indian Ocean, the global circulation that is observed across the entirety of the ocean, the global conveyor belt, the Atlantic meridional overturning circulation, the Sargasso Sea. These are the portions and the coral reefs we will be covering after the lunch break. So take a lunch break now, and the break will continue till 3:45. Break till 3:45 p.m. Okay. See you after the break, and we will continue.